Welcome back. How are you doing? Moving on over right here. So I'm reminded that as as your career progresses and you realize you've given the same lecture, what, more than 50 times? The first time you want to make a video of the lecture is the first time you're going to forget that, yes, it's the willow tree that has salicylic acid in its bark. And I don't know why I forgot that. I'm not going to be hard on myself. This is one of my favorite mechanisms. It incorporates a lot of stuff that we've studied previously, and it's got our new stuff with aromaticity and things that aren't aromatic all of a sudden happening as well. If you took phenol and we oxidized it to try to oxidize this to a carbonyl, you get a new carbonyl also on the para position. How can that be? Well, you're stuck. You say, I know how to do the chromic ester oxidation in my sleep. Let's just start off with that. You first start by protonating the chromic acid to activate it towards the attack by the weak nucleophile alcohol. And then you generate this oxonium, which needs neutralizing. And then you strip water off of this to make a chromate ester. Yes, that's a chromate ester. Pen is off. Chromate ester. Probably right under my head. Chromate ester. And the chromate ester right here oxidizes in a strange way. What we see is we don't have an H to remove here like we normally do to make a carbonyl. This is an sp2 carbon without an H there. But resonance can happen to generate the pi bond and make chromium reduced. Chromate ester has chromium plus 6. HCr3 is a more stable version, but still not stable. Chromium plus 5, it reacts further, but we never look at that part of the mechanism. Hey, this generated a carbocation in a aqueous environment. Look, aqueous environment. Carbocation, what's going to happen? Water attacks it. I could have combined these two steps, couldn't I? Water attacks and then the acid-base reaction to neutralize the oxonium. You can do that on a test if you want. Black arrow first, and then these would be gray on the same H over here. And then, hey, chromic acid oxidation number 2. This is a normal alcohol this time. It's got an H on this carbon. So you follow all the steps to make the chromate ester, which is right here. And you can remove the H as we normally do. And we make what's called a quinone. Quinone. Why would we make a quinone? Why are quinones special? That's a good question. Why are quinones special? I guess that's question number 2. Question number 1, what's a quinone? We have paraquinone, which we wrote up there. You might think they don't belong in this chapter because they're not aromatic, and you would be correct. This is para, and its ortho brother is a different molecule. Has adjacent carbonyls and pi's here and here, and a very strange looking extension here. There we go. Orthoquinone. Well, quinones are stable in that they have two carbonyls. Carbonyls, pretty strong pi bonds. But they're also unstable because they lost their aromaticity. The benzene can't go around in a circle just to resonate outside the circle. It's not aromaticity when you're resonating outside the circle. That's just normal old resonance. So they've lost their aromaticity and they're still fairly stable. I guess that's why they're special. Even though they've lost their aromaticity, they still have fairly stable pi to oxygen. So they've got some positives and some negatives. And here's quinones all over the place. So we talk about a molecule like ubiquinone, which has a really cool name. It's based on this word, ubiquitous, which means found everywhere. And quite simply, it's a very well-named molecule. By everywhere, we mean if you're a living organism, any living organism, you use ubiquinone on a daily basis. Yes, every living organism. So it is found in every living organism. And there's substantial amounts of the quinone and the dihydro version of it. Where does the word dihydro come from? Well, if you look at the species, the only change in the formula is two extra hydrogens that were not there before. And yes, the pi electrons had to shuffle. And we can look at the lab version of that reaction here. If we used hydride, we could do what's happening in nature down here. Hydride attacking for the first and only time ever an atom other than carbon. The reason being, good question, why? I thought we would attack the more positive carbon. That's what we've been doing our whole lives. Why are we attacking that negative? That's a very large-eyed, sad person. Why are we attacking the negative atom? Well, the reason's quite simple. Look, the benzene structure here is aromatic. This is the only way you can get your aromaticity. So sometimes we go against our normal intuition to achieve a very stabilizing result of aromaticity. And then step 2, you just put the proton on there and you get the dihydro version of the quinone. Why is it very stable? It's got aromaticity. This has stability due to very electronegative oxygens participating in pi, but it doesn't have aromaticity. So that explains the question, why do we have substantial amounts of this and this at all times in every living organism? Yeah, well, this has nice, strong carbonyl pi bonds. That's good, but it's not aromatic. That's bad. This thing's aromatic. That's good, but it doesn't have carbonyls. Not quite as good as you would normally think. What are these appendages over here? If you're a mammal, there's a chance you have 10 of these, which would be a pentaterpene. Think about that. Yeah, this molecule, I used the word terpene. I just threw that in there. Hey, it's a group that goes 1, 2, 3, 4 with a branch off of 2, and it repeats. So that part of the molecule is a terpene. Ubiquinone is not called a terpene, though. It's called the majority of it is a terpene. Oops, that's just going to look bad. Terpene oid. Oid as a suffix means like or ish. This portion over here does not qualify as a terpene. It's the business end, by the way, of ubiquinone, but the majority of the molecule is based on a terpene. So terpene chemistry was used to make the tether over here. And why does it need that big long tether? Well, we want ubiquinone to stay trapped in the area where it does its stuff. And we don't want it wandering around into the cytosol, which is the solvent of a cell, which is always water. So these molecules are not water soluble at all. The majority of it is just C's and H's here. Only a small portion of the molecule is polar. So that makes it sit still. It doesn't go into an aqueous environment. And what are these molecules? NADH becoming NAD+. Well, the H's are hydrides, and they went onto the quinone. And NADH is over here, and NAD is here in its full form. And it's a good discussion all by itself. In your body at all times, any living organism, you also have substantial amounts of NAD+, which has the bonus of being aromatic and has the detraction of being a cation. And you have roughly equal amounts at any given time of NADH, which is no longer aromatic. It has an sp3 atom down here, but it doesn't have a charge. There's always a good and a bad in both of these. That's why we have roughly equal amounts at all times in our bodies. And these are all redox reactions. NADH gives up its hydride to the ubiquinone, and it becomes hydroubiquinone. And if it wants to take it back, NADH will become NAD+. I think that's backward. There's a typo. Hasn't been spotted. It's a brand new book, guys. But nobody spotted it before. This NAD+ is going to accept the hydride from the dihydroubiquinone, and it's going to become NADH. Oh, yeah. NADH. Okay. And this is all part of the electron transfer cycle that you study in biology, but we're getting into the chemistry of it, aren't we? Okay. So you're responsible for all the mechanisms on this page and knowing a little bit about ubiquinone and NAD+ and their reduced partners, dihydroubiquinone and NADH. And I'm going to finish up pretty soon. We're going to look at reactions at the benzylic position and why are they so special? Why do they happen quite easily? And the answer is the benzylic position, even if it's an unstable cation or anion or radical, the benzylic position, just like the allylic position, is stabilized by what? By resonance. And we have all the resonance forms for benzylic cation, anion, and radical here. And we see when we resonate from the benzylic position to this, that the cation ends up in the ortho position, one away from our methylene here. And if we do a further resonance, the cation ends up on the para position and further gets the other ortho. One of our words from nomenclature is not showing up on this page at all, is it? Where's the cation never? It's never here, which is meta, because resonance won't allow that. So resonance of benzylic cations gives orthocations and paracations. Anions, same story. Arrows look a little different. You flow away from anions. You flow towards cations. For obvious reasons, these are electrons. Electrons are attracted to cations, and anions are pushy. They push away from them. Ortho anion, para anion, ortho anion, back to a benzylic anion that has the resonance form of benzene. Radicals, you got to use hooks. These are hooks, not arrows. And same story, ortho radical and para radical and ortho radical. And how can we take advantage of this? Well, we can do reactions that we've never seen before, but keeping in mind that a cation is fairly easily made here. How do you know a cation is fairly easily made right here? Well, the product is resonance stabilized. So generation of a cation happens under these conditions. Dichromate looks familiar. Sulfuric acid, water, and heat. The heat's very important here. Without heat, you get nothing. No reaction. If you have a benzylic carbon with at least one hydrogen, at least one. Here we have 3. We have an abundance of hydrogens on the benzylic position. You will oxidize that carbon all the way to a carboxylic acid. That happens here. It happens here when we have 2 H's on the benzylic position, and it happens to both of those carbons at the benzylic position. I don't care about the side products. Those are also carboxylic acids. In this molecule, we're going to do it here. Got 3 H's in the benzylic. Here, 2 H's in the benzylic, and here none, which means no reaction. So don't react a benzylic carbon under these conditions if there's no H on it. And these are the same conditions, believe it or not, as over here. It's just different ways of generating chromic acid, which we already know. No H, no reaction. H's, benzylic oxidation. No H, no reaction. H, 1 H is all you need. You get a benzylic oxidation, and you get 2 of these to become methanoic acid or formic acid. But I don't care about the side products. We're not going to make you responsible for that mechanism, but you need to know that it happens under these conditions. And when it happens, and when it doesn't. And it's pretty straightforward, isn't it? When does it happen and when doesn't it? And one of our final topics, looking ahead, do we have enough time? Yeah, that one just takes a few minutes and it's more fun than chemistry. Okay. So what's going to happen here? We want to oxidize a aldehyde without oxidizing an alcohol. We could use our old friend DHP to protect the alcohol, but then you got trouble. Do you know why you have trouble? Here's the protection step. You're trying to protect your alcohol so you can react your aldehyde. Well, sadly, the conditions of oxidation are also the conditions of deprotection of a DHP protecting group. Deprotection of DHP happens under acidic aqueous conditions. So acidic aqueous conditions are going to deprotect your alcohol and it will get oxidized. And of course, your aldehyde will also get oxidized. So you get stuff you want to happen. Your goal is to make the oxidized aldehyde, but not to make the oxidized alcohol, which is here. And we need a better protecting group, one that doesn't deprotect under the conditions of oxidation. And a good example is a benzyl ether. Benzylic ethers can undergo hydrogenolysis. It's an easy method of deprotecting them. Benzylic ethers are what undergo hydrogenolysis. So how do you make a benzylic ether? Well, deprotonate your alcohol to make a nucleophile and attack it with benzyl bromide, and you have a benzylic ether. That's straight up acid base followed by SN2. And then you can do your oxidation of your aldehyde. Oxidation of your aldehyde, your ether will not be touched. You don't need heat during this reaction because aldehydes are easily oxidized with chromic acid. And then what happens during hydrogenolysis is exactly what the name says. You're going to lyse the benzylic ether and put a hydrogen on each side. There's your hydrogens. Why does this happen? It's because the benzylic bond is weak. It can stabilize if the reaction involves radicals, anions, or cations, and you don't even need to know the mechanism for this reaction anyway. Just know that this will happen if you have a benzylic ether attached right here and cuts. There's your new H's, and that's our target for today's hydrogenolysis demonstration. And it's a good method of protecting alcohols and then quickly deprotecting. It's very, anytime you use hydrogen in a catalyst, that's one of your cleaner reactions. Very easy to do in the lab. And then the cleanup involves just filtering away your catalyst and store it so you can use it again later. But this is not a lab course. We shouldn't focus on such things too extensively. And the last part has to do with just NMR, so no more chemistry. Looking at proton NMR. And then we just remember what happens to a benzene when we turn on an electromagnet. Okay, so you have your benzene here. That's this molecule right here. Looks like I drew the double bonds here, here, and here. And I showed their p orbitals up here. And you turn on the electromagnet. Applied magnetic field is the electromagnet. And then the pi electrons start resonating in one direction only to take advantage of an attraction to the magnetic field. It's sort of like your north-south poles lining up in magnets. Even if you turn on your electromagnet in one and you have the other one like this, it's going to flip so it can be attracted and stabilized. So all the benzenes will realign themselves to resonate this way. And when they do that, they cause their own magnetic field. The circularly rotating electrons that you just caused cause their own magnetic field, and the magnetic field follows the is it the left-hand rule? Left-hand rule, it's electrons, right? Anyway, I'm not going to make you get into details. This diagram took me forever to draw. Let me try to summarize quickly what it's trying to say. These rotating electrons cause this magnetic field, and it comes out the bottom of the benzene, this magnetic field, and it comes around. There's one of the field loops. There's another field loop. And this field loop, it intercepts this hydrogen. And when it comes to the hydrogen, what direction is it pointing? It's pointing the same direction as the applied magnetic field. So it's adding to the strength of the applied magnetic field. And remember what happens then? You cause a bigger energy gap between the two spin states. Remember, nuclear magnetic resonance is spinning this way, resonating with spinning the other way. Well, you cause a bigger gap, which means the numbers are much bigger. And we already knew that. We just didn't know why. The numbers went up to 7.1. I mean, that's a big number. That's not the normal number for, say, an alkene, H. And it's because of this effect here. The induced magnetic field by the pi electrons in this donut shape, I know it's a little hard to see it, but imagine a donut there, is in the direction of the applied magnetic field when it encounters these hydrogens. And I'm going to leave you with this question and answer. If benzene had an H in the middle, which it doesn't, but if it did, what direction is the induced magnetic field of the pi electrons facing? If there's a hydrogen there, it's going against the magnetic field. Well, in larger molecules like 18-annuline, there is an H in the middle. And this H on the outside has an even bigger pi cloud, because there's a lot more electrons resonating in a bigger circle here that causes a bigger force. So these go up even higher than 7. And the ones in the middle of the benzene, our concluding comment, the H is in the middle. It's not a benzene, sorry. The H's in the middle of this big aromatic compound have a negative ppms. You've never seen that before. It's because this arrow is working against the applied magnetic field rather strongly. And yeah, so we call that an aromatic effect in the middle of the benzene, or whatever the aromatic is not benzene. I keep saying that by mistake. But H's in the middle of a big aromatic will be negative. H's on the outside, of course, will be large because of the induced pi electron magnetic field. And I have run out of time. So I will talk to you on Wednesday. And I will see you then.